In this video, I will talk about the idea of image compression. First, I will discuss why image compression is required. Then I will come to the point that how image compression is even possible. So in order to understand the point that why image compression is required, suppose we can take an example of a color video of 2 hour duration. Okay. So we know that each hour is 60 minutes and each minute is 60 seconds. So the total time of the video will be around 2 into 60 into 60 seconds. Now suppose that the image, that is the video, is changing the frame at a rate of 30 frames per second, which means that the video is actually showing 30 different frames in every second. Now suppose that the frame width and height of my video is around 720 by 480 pixels, which means that horizontally it has 720 pixels and vertically it has 480 pixels. And each of these pixels are color pixels or color, it is a color video, so we will require three different numbers or 3 bytes to store the pixel value of a single frame. Suppose that this is your video frame and you have 720 pixels here and you have 480 pixels here. So this is a color video, so which means that I will have to store the red channel as well as green channel as well as blue channel. So each of the frame will have 3 different integers to store the intensity of each pixel. So a single pixel in the color image will have 3 different values in the red, green and blue channels. Okay. And so this is the actual number of bytes. So this 3 is the number of bytes required to store the intensity of a single pixel. So if you calculate this number comes around 2.24 into 10 raised to 11. That means that if you convert that into usual data size representations, this will be around 224 GBs. And if you take this number into perspective, then suppose that you have an 8.5 GB video, then in order to store a single video you will require around 27 DVDs. And more than that, moreover, if you want to stream this video through Netflix or Amazon Prime, then it will be taking a lot of memory from your bandwidth, so that it will make the viewing experience even impossible. These facts shows that we should have certain methods to store the signal in a compressed format rather than storing it in the original size. So in order to store the image or to store the signal, or as well as if you want to communicate the signal through some communication channels, then there should be some method to compress the data in one end and decompress the data on the other end, so that the data transmission from one end to the other end can be reduced, so the communication or the storage will be more efficient. So this is the idea, uh, that we should have certain methods to compress the signal, especially video or image. Now we will look at the fundamentals of data compression, which is applicable for image compression or audio compression or any compression related to any signal. So first of all, we need to look at what is data compression. Data compression is the process of reducing data required to represent a given amount of information. Okay. Data compression is the process of reducing data required to represent a given amount of information. So we are talking about two different terms here. One is data, another one is information. We may have used these two terms interchangeably, but in this definition these two terms has got its own specific meaning. So data is something that we use to represent an information. If you can reduce the data that is required to uh, represent a given amount of information, then that process is called data compression. Suppose that you need to store, let's say, some numbers like 0, 1, 2, 3. These are the numbers that you need to store. If I am using an 8-bit representation, so this number will be 0, 0, 0, 0, 0, 0, 0, 0, and the second number would be 0, 0, 0, 0, 0, 0, 0, 1. Then I have 0, 0, 0, 0, 0, 0, 1, 0. Then the last one will be 1, 1. So this can be data and this can be an information. So information is the same 0, 1, 2, 3, and I'm using this data to store this specific information. Now suppose that if I am using another data to store the same information, let's say, so you can see that you are storing numbers only from 0 to 3, and you are quite sure that the number will not go beyond these these four numbers. Then there is no need of using these many bits to store the data information. So what I can do instead is I can just use 2 bits to store this information. So 0, 0, 0, 1, 1, 0, 1, 1. So, okay, so this is another data that is used to store this information. So you can see that if you have used uh, 8 bits here to store a specific number, here I'm just using uh, 2 extra zeros, I mean 2 zeros only. That means I'm storing only with 2 bits. That represent that I don't need these many 6 bits extra to store my information. I can do it with 2 bits only. So actually what I'm doing is I'm storing the same information, but using two different kind of data representation. So if I go to the in terms of compression, I can actually compress this data into this form that makes the amount of data required to store this information. Okay, and one term that commonly used to measure the effectiveness of data compression is the compression ratio. So this B, you can take this B as the number of bits before compression, and this B dash can be taken as number of bits after compression. Okay, I'm using this before and after to get an idea about what compression ratio is giving us. This cannot be before or after, it can be just two different times. So B represents the number of bits in one format, and B dash represent gives the number of bits in another format. So that doesn't mean that this should be always before and after, it can be other way around also. But I'm using these terminologies to give an idea about uh, the compression ratio in an easy way. Suppose that if I'm saying that this compression ratio C is actually 10 by 1, or it is 10 is to 1, then what it represents is 1 bit is enough to store 10 bits of the uncompressed data, right? So what means this means that after compression I just need 1 bit to store the same amount of information. Before compression it was 10 bits. Okay, that means that 1 bit, or in other words 10 bits can be replaced just by 1 bit. If you take this example, you can see that 8 bits can be replaced only by 2 bits. Okay, so you can see that these numbers, these 6 bits are not actually required to store this information. Okay, so you can say that these 6 bits are actually redundant. Okay, So what we will do is, actually if there is some redundant data in the information, then we can utilize that redundant data, or we can exploit that redundant data to make the data shorter, that makes the compression possible. So in order to measure how many data are redundant in a particular representation, we will usually use the term relative data redundancy. So relative data redundancy is given by the equation R is equal to 1 minus 1 by C, where C is the compression ratio that we have discussed before. So suppose that if for the same case, for example, if I have C is equal to 10 by 1 or 10 is to 1, then I will calculate the value of R as 1 minus 1 by 10 by 1, or it is equal to 1 minus 1 by 10, or it is equal to 0.9. So this number 0.9, if I convert that into percentage, then this will be around 9, it will be 90 percentage. That means that before compression 90 percentage of the data was redundant, and after compression we can just represent by using a single bit, where it was actually represented by using 10 bits before compression, which means that in the previous representation 90 percentage of data was redundant, or which was actually unwanted. Okay, so these are the two major terms that we need to discuss while discussing the topics related to data compression. So compression is the process of reducing the data required to represent a given amount of information. So you have to understand the difference between data as well as information. Data is the way of representing certain information. So I can have several kind of representation. So data compression means we just want to get the minimum amount of data to represent an information. And compression ratio is the ratio of number of bits in one format to the number of bits in another format, or in another way of representation. To get the idea into perspective, you can use the B as number of bits before compression and B dash as number of bits after compression. So if I say C is equal to 10 by 1, or if I say C equal to 10 is to 1, then you have to understand that 1 bit is enough to store 10 bits that was used in a format before compression. Relative data redundancy is giving us what percentage of the data was redundant, or it was actually unwanted. So we are finding that number using this equation, that is R is equal to 1 minus 1 by C, which is equal to 1 minus 1 by 10, or 0.9. If I convert that into percentage, it is 90 percentage. That means that 90 percentage of the data used before compression was actually unwanted. So we can exploit that unwanted data to make the data representation shorter. That makes the conversion, that makes the compression process possible. Now we'll look at what are different types of data redundancies, or we will answer the question how data compression can be done. Okay, so there are three different types of uh, data redundancies. The first one is coding redundancy. Coding redundancy. Okay. In order to explain the coding redundancy, I have taken an image and its histogram values. So I will come to that point. So if you look at this image has only 4 different intensity values. I have these lines with an intensity of 255, and I have this star with an intensity of 186. Then I have the background, the major background, the gray shade of intensity of 180, 128. Then there is a dark region with an intensity of 87. So this image consists of only these 4 intensity values, and no other intensity values are present in this image. So those are the values that I have listed under the value R subscript K. Then if you look at the probability of those intensities in the image, you can see that 25% of the intensity values are of value 87, 47% are of value 128. That is the major share in this image, that is this gray shade. Then I have a very little value of 255, that is a complete whitish region with only 0.03 percentage. This is actually the probability, and you can see that all other values except these four intensity values has got a contribution of 0 percentage. Now suppose that if I am using an 8-bit code or the usual byte representation in order to represent each of these intensity values, then I will be consuming 8 different bytes in order to store the image of this kind. Now if I map this 87 number 87 value to a representation or the data representation of 0 1, and the 128 value with the data representation of 1, and this 186 value to a data representation of 0 0 0, and 255 value with the data representation of 0 0 1, then you can see that this 0 1 is taking only 2 bits length, and this is taking only 1 bit, this one is taking only 3, and this one is taking only 3 bits. So before it was we were consuming 8 bits to store each intensity values. Now we are taking different length bits in order to store the intensity values. Now imagine that uh, this image is a let's say a 100 by 100 image. Then each of these intensity values are represented by 8 bits. Then you can say that I will be consuming this much of data, which means that I will be consuming 100 into 100 into 8 bits of data in order to store this image. Now on other words, if I am taking only 2133 length bits to store my image, then you can see that this 2 is 25% of the data is taken by this 2. So you can do the math. 0.25 into 2 plus 0.47 into 1 plus 0.25 into 3 plus 0.03 into 3. So if you do this calculation, you can see that only 1.81 bits will be used to store a single intensity. Okay, or in other words, if I have a 100 by 100 image, if I have a 100 by 100 image, and if I multiply this one with 1.81, this much space will be utilized in the computer memory in order to store this number. So you can see that this is approximately more than 4 times the space required to store an image with this kind of representation. So that is how we can make use of the coding redundancy in order to compress an image, where we will be shortening the number of bits used to store a intensity value in the image so that we can make the image compression more efficient. Well, this is one way of doing image compression. And the second type of redundancy is called the spatial redundancy or temporal redundancy. In spatial or temporal redundancy, what we are looking at is we are looking at a pattern in the spatial domain. So for example, if you consider this image, you can see that we have several horizontal strips of line where the intensity value does not change in a single line. And this is applicable for all lines that you can see in this image. So imagine that if I have, let's say, 100 pixels horizontally, then if I am using 8 bits to store each of those pixels, then I will be consuming around 100 into 8, 800 bits to store a single line. In other words, imagine that if the intensity value of this particular, the first line is, let's say, 5, that is the intensity value, then I am making a coding convention that whatever number I write next, that will be the length of that line, or in how many pixels that number is going to repeat. So if I write 5 comma 100, what does this represent? That is, the intensity 5 is representing in the coming 100 pixels. So that is one way of writing. For example, if you suppose that the next line has got an intensity, let's say 255, and suppose that I have a suppose that I have again the complete line is represented by 255 value intensity, and that also lasts for a duration of 100 pixels. Then from only from this data I can interpolate, or I can recover the entire line. So if you look at this one, 5 comma 100 means I have a back line of 100 pixels. 255 comma 100 means I have a white line of 100 pixels. So rather than having 100 into 8 plus 100 into 8, that is around 1600 bits to store two lines. Suppose that if I'm using an 8 bit for this one, 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 that gives us a value 32 bits. Okay, and this gives us a value 1600 bits. So you can directly see that there is a reduced amount of data to store the same value of information, or same amount of information. So this is how we make use of temporal or spatial redundancy in an image. The third type of data redundancy is irrelevant information. So in order to explain the idea of irrelevant information, you just look at this image. This image has got a grayish color all over the image, and if you look at the histogram, this is the histogram of that image. So you can see that the major contribution to this image comes from a intensity level or a gray level, that is between the complete darkness and complete brightness. Well, let's say that intensity value is 128, but this image also got some intensity values like 129 or 120 or 130. That is, that you can see that we have one intensity at top, and some contribution from the adjacent intensity values are also present in this image. And I can go to the other side also, I can have intensity values like 127 or 126. But if the application allows us to have only one intensity, for example, if this is for some human visualization, or for some human inference, for a general purpose application, then by getting all this intensity value in this particular image will not make any significant difference for a viewer. Even though if I represent this entire image only with one intensity value 128, that doesn't make any difference to the viewer as far as this image is concerned. And even though if I include this one, that does not make any change to the viewer's interpretation from this image. So in irrelevant information, what we are doing is we will be just neglecting the information that are not relevant or that does not serve any purpose. So I will be, in this particular example, I will be going for representing this entire image by using a single intensity values 128. And in some applications, if you want to preserve the histogram like this, or if you want to have those small intensity values in this image, then we will not be able to exploit the irrelevant information from that image. So if the application allows us to have the irrelevant information removed, then that will be uh, helpful for us to exploit for data compression. So this is the idea of irrelevant information. I hope this is clear. Thank you very much.